Last thing we're going to see from this section is a discussion on unions of finite sets. Specifically, we're going to be looking at the cardinalities or cardinal numbers of these kinds of unions, where the main thing to bear in mind is that when we're taking the unions of finite sets, we're not talking about exclusive OR. So we're not talking about addition where we exclude stuff that's in both. We should be careful about what happens when there's overlap. Let's take a really simple example. Let's say A is equal to the set 1, 2, and B is equal to the set. So looking at that, if you took their union, it's pretty easy to see that A union B would just end up being 1, 2, 3. Everything in A, everything in B, 1, 2, 3. And if we wanted to take the cardinal number of that, just get 3. Pretty easy, okay? But if you went back here and you thought about this, you'd say, okay, well, unions act a lot like addition because we're saying OR, so we're just taking all of our possible options. So if we looked at A, we've got 2 things. If you looked at B, we've got 2 things. So if you took both of them together, it might have made sense for them to be 4, but obviously that's not the case. And the reason for that is the overlap in the middle. The general rule for dealing with unions of sets, for finite unions of sets, is that if we take the cardinality of a union, the cardinality of A union B, we get cardinality of A plus the cardinality of B minus cardinality of what is in both, minus the cardinality of their intersection. And the reason for that, I'm not going to give a strictly rigorous proof, but I'll give you the general idea of how this works, is when you count A, you count all the things in A, then you count all the things in B, but here you're counting all the things that are in both, and here you're also counting all the things that are in both. So in order to make sure that you don't overcount, you've got to knock out 1. And to make sure that we understand this, take a quick look at an applied example. For here, we're given the statement that a pet store surveyed shoppers, finding that 96 owned cats, 97 had dogs, and 29 had both. How many people owned cats or dogs? A pretty basic setup for this type of problem. What we want to find is a cardinality. So, we're looking for here is first, you gotta define the sets that we're actually working from. So let's set some notation. Let's say that A is the set of dog owners and B is the set of cat owners. Now we gotta play some games with the cardinalities here. So what we're gonna do is notice that from the given statement, cardinality of A, the number of people that own dogs from our sample, is 97, while the cardinality of B, the number of people that own cats, is 96. And there's a very important there's a very important number that's given in here as well, which is the number of people that own cats and dogs, the number of people that are in the intersection of these 2 groups. That is given to be 29. So when we're counting the 97 people who own dogs, this 29 is included, and this 29 is also included when we count the number of people that own cats. Because if you own cats and dogs, you own cats. And if you own cats and dogs, you own dogs. So both of these groups count that group as well, which means if you want to count up the total number of options, we have to be careful not to count this one twice. That is to say, if we want the cardinality of the group of people who own cats or dogs. That is to say, we want to find the number of people who own cats or dogs. We need to look at the number of people who own dogs, plus the number of people who own cats, minus one count of the number of people that own both, because each of these first two groups already accounts for one. So, we get 97 plus 96 minus 29, for a total of, assuming I can do math, 164 people. So, 164 people own either a cat or a dog. Sample.